Hi, so today we're going to talk about what is a force. So if you think back to past science classes, a force was probably defined as any push or pull. So there's a couple rules when we start naming forces. We have to take a couple things in mind. So when naming forces, you must name the physical object doing the pushing or pulling. So if we think about gravity, gravity is nothing that you can actually feel or touch or nothing that's really tangible. So there is something that is causing this gravity, and it's the earth. So if you have two things that have mass, there's going to be attraction between those two masses, and there's going to be this attractive force trying to pull those two masses together. So you have mass, the earth has mass, but the earth's mass is very extremely different than ours. So we are influenced by Earth's gravitational field. So it's Earth that's causing this gravity. So when we're naming the force, we don't want to say gravity because gravity isn't a physical object, it's Earth. So Earth is a physical object that is pulling down on us, not gravity. So there's two types of forces, non-contact forces and contact forces. So non-contact, I think of things that are not in contact, they are not touching. Contact forces, things that are touching. So there's three types of non-contact forces. Number one being gravitational, that's the only one we're going to focus on with this unit. Then there's electromagnetic and static. So a gravitational is the force exerted by any object that has mass. So like I previously mentioned, the Earth exerts a strong gravitational force on us because of its large mass. So if we're not on Earth, if we're on the moon, then it's going to be the moon's gravitational force on us because, again, even though the moon is smaller than the Earth, it still has a extremely large mass compared to us. So there's less gravity or less pull downward on us on the moon, but there's still some there. So that's always going to be, I asked you to draw a diagram of the forces on an object. You're always going to have one non-contact force, which is gravity or Earth's pull. Unless there's a situation where the problem says you are in, a gravity-free environment, and then that's one scenario that you wouldn't have that downward arrow. And then electromagnetic, you can think of magnets. So if you have the two opposite sides facing towards each other, even when they're not touching, when they're close, you will feel this attractive pull trying to get those magnets to come together. If you flip them around and they have the same sides facing each other, you're going to bring them close together and you'll feel this repulsive force trying to push them apart. And then static, this is what we're going to talk about when we get to electricity at the end of the school year, charged particles. So if you think back to chemistry class, opposite charges attract, like charges repel. So we'll be doing labs where we can transfer electrons to things or take off electrons and see what happens when they're brought to like charges, opposite charges, neutral charges. So we'll talk about that later on. So contact forces, it's just whenever things are touching one another. So two objects are in direct contact with each other. So this includes friction and air resistance because those both involve contact on a molecular level, but it's still things that are touching. So if I ask you to tell me what forces are being exerted on an object, we're always going to have our one non-contact force, which will be Earth's pull or gravity. And then you ask yourself, well, what is in physical contact with the object we're focusing on? And then if something's in touching it, then we're going to label that with a vector in the direction that the push or pull is being applied. So we have these things called force diagrams, or you may see them written on worksheets, or I'll maybe say free body diagrams. They mean the exact same thing. So back when I had you do that survey, that misconception survey at the beginning of this unit, the very last question asked you to draw a picture of a person pulling a sled and show all the forces acting on that sled. So instead of actually having to draw an actual picture of everything, there's a little simpler way that we can do this to show what forces are being exerted on an object. So instead of drawing the actual object, you'll just use a dot. So the dot is to represent the objects, so you don't have to draw the picture. Then we know forces are a vector. They have magnitude and direction. So we're going to draw arrows, and our vectors have a head and a tail, and we also need to label them, and we'll talk about how we will label them in a little bit. And we also need to remember that the length of the vector matters. So when we talked about velocity, if something had a greater velocity, you had a longer vector. Same thing with force. If there is a greater force, it needs a longer vector. So if you have a 10 Newton force on an object and also a 5 Newton force on an object, I would expect that that 10 Newton force vector was twice as long as the 5 Newton force vector. We always are showing the direction of which way the push or pull is being exerted on the object. So the head always points away from the dot. So if something's pulling something up, you'll have our dot and then an arrow pointing up. And if it's pulling on even on an angle, it could be pulling, 30 degrees north of east, and we'll draw it in that direction. So it's always away from the dot. And then the force diagrams show all of the forces acting on the object. So we talked about we had contact and non-contact forces. So we will always include both of those. Again, we should always have our one non-contact force, which is gravity. And then again, you ask yourself, what is in physical contact with our object? And then you will draw them, put those vectors on your force diagram, and we will label them. So how we label forces is, I call it the agent-object notation. So there's always an agent causing the force on an object. So the agent is the thing pushing or pulling on the object. And when we do these free body diagrams or force diagrams, we only focus on one object at a time. So if I'm standing here and I have a book, I'm holding up a book with my hand, and the book is at rest on my hand, I'm not moving my hand, we would have this force diagram of, we start off by drawing a dot, and then, so here's my dot, and then we draw our vector. So we always have our one non-contact force, which is Earth's pull or gravity. So Earth always pulls down, so I have my vector going down, and then I ask myself, well, what's in physical contact with the book? And probably 98% of the time, we're going to exclude air resistance. The only time to include air resistance is if the problem specifically says to include it. So the only thing else that's touching the book is my hand. And which direction is my hand exerting a force on the book? And it's up. So then we have our vector up, and then we label our vector. So we always start off with a capital F, and then you label it with the agent first and then the object second. So since for Earth's pull down here, I labeled it FEB. So that would read the force of the Earth on the book. Earth being the agent, and the book obviously being my object. And then for my vector up, the force of the hand on the book. The hand being the agent, and the book being the object. And you notice that the second letter is the same, and that's how it will always be, whether you have one force or 10 forces on a force diagram. The second letter will always be the same letter, because again, we only focus on one object at a time when we do these force diagrams. So like I just previously mentioned, this FEB would read the force of the Earth on the ball, or the book. We did a book, and this is also known as weight. So if I ask you what is the weight of this object, if we knew how much the Earth was pulling down on an object, we would know the weight of the object. So if you look in this example, this force diagram that's drawn here, you can also, I mentioned before that the length of the vectors matter. So if you look here, the vectors are the same length, which means they have the same magnitude of force. So if the force of the Earth on the book was 10 newtons, then my hand must have been exerting 10 newtons up on the book, because the book was at rest on my hand. So if we have 10 newtons down and 10 newtons up, the forces cancel each other out, and we say we have a balanced force diagram. So just practicing doing some of this agent-object notation. So if I said object A was exerting a force on object B, we would write that F force of object A on object B. So we have always a capital F, and then like down in subscripts, you write the agent first and then the object second. If I was pushing on a wall, we could say the force of the person on the wall. If we were to write the force of the book on the table, we would say FBT, the force of the book on the table. And then if we had a balloon that is being held by a string, we would say the force of the string S on the balloon. So friction, since friction starts with an F and force starts with an F, there is another way that we write friction when friction is applied on certain situations. So we write the frictional force with a lowercase f, and we consider the two objects that are in contact. So if we're considering a box sliding across a floor, obviously there's friction between the floor and the box. And so we would write that force diagram as lowercase f and then capital F and B. So that would read the frictional force of the floor on the box. So the one thing again, just with friction, just remember it's always a lowercase f first. So if we think about what forces are acting on you when you're sitting in your chair, so we always know, we got to think about our contact and non-contact forces, and we know we always have one non-contact force, which is going to be the force of Earth's pull, and then you ask yourself, well, what is your body in contact with? And you could say, some people usually say the seat, and then some people say the seat and the floor. So we'll do both examples. So if we just look at you and the chair, we need to think about, do we want a balanced or unbalanced force diagram? So if you are at rest, then we want it to be a balanced force diagram. So we start off by drawing our dot. And then we have the force of Earth's pull, which is always down. This is the force of Earth on your body. And then you have the chair. And so you're not going down into the ground or down into the seat. So the Earth is not pulling down on you any more than the chair is pushing up on you. And vice versa. The chair is not pushing up on you more than Earth's pulling you down. If that's the case, you'd be going up in that direction. So we need a vector up the exact same length as the arrow we drew down. That's the force of the chair on your body. So here we have a balanced force diagram. You're at rest. So some of you that may said, well, it's the chair, my feet are touching the ground, so then the ground also must be applying a force on you. So again, we still have the amount of Earth pulling down on you. The chair is going to still push up on you, but if you also have an additional force, you have to take some things into consideration. So you ask yourself, well, how is the ground applying a force on your body? And it would be up. So if the chair is pushing up on you and the ground is pushing up on you, we would have two vectors up. And there's a specific way I would like you to draw if there's more than one vector in the same direction. So in this case, if you have two vectors up and you're still at rest, we need a balanced force diagram. So the chair is not going to push up on you with the exact same amount of force in our first example over here on the left, because now you have another force pushing up on you. So we don't need as much as this vector is. So we're going to draw the force of the chair on your body.